Welcome to part 3 of my How Async Internet Works videos. In this one we will cover the actual meat of the issue, how async and C# actually works, and we're going to look into some of the threading issues that come with it. So, let's just talk about the concept of async. So this bit is completely generic and it applies to C# and JavaScript and various other languages. So the idea is that you have a program and it says, hey operating system, can you just do something for me? And the operating system goes, yeah, of course I can. Just, tell you what, I'll do the work, and then when I'm done, I'm going to give you a call back. So just tell me, what code to call, and I'll run that when, or tell you to run that when I'm done. And your program, well, you don't do this, but something in your program will save the state somewhere, and then it just forgets about it, okay? And then the operating system, quite important in your program at this point, there is no threads of any kind, there's no pointer. There's some state saved, but you don't have any like lightweight threads or anything like that allocated that sits there. It's just, stored somewhere. Now, the operating system goes ahead, does the work, and then at some point it says, yeah, I'm done. And it says, hey program, I'm done. Give you a call back and say, I've done the work you asked me to do. And your program then has to load the state back and then run the callback code. So you can probably see that there's a fair bit going on here. There's a lot of complexity that is hidden from that little await keyword and the async keywords. They hide an awful lot of logic that happens underneath that. So to try and explain what really happens is that this is really about the compiler rewriting your code. So if you were a bit old school, you might have had to write async code with callbacks. Both in JavaScript we used to have it, and in C# we used to have it. So, and actually underneath the covers, it's still callbacks. It's always a callback. So this is the code that you might be writing. So we create an HTTP client, then we have an async call here, and then we have some code that we want to run when we have the result of that thing. So we're going to compute the links of the HTML. So what the compiler will do, it will rewrite your code to something like, it's a lot more complicated than this, but in principle, it looks a little bit like this. So it'll create a task, it will create a task for you, a task object, and there's a method call in there, and then there's a callback. So it takes your code here, and it wraps it up into a callback that takes the return value from this method call. And that becomes the callback that, when you're calling out to the operating system and say, please do this thing and come back to me, this is the callback that will then eventually be called, and the state will be loaded up. So if there were any instance variables or captured variables, they would have been captured at this point. Again, all very simplified, but it's really important to understand, which is why I'm laboring it so much, that your code gets rewritten by the compiler. The whole async and await stuff doesn't exist at runtime. Your code gets rewritten into a state machine, and if you actually were to crack open the IL, you'd see something like that, but just a lot more complicated. So the other thing that I want to just explain is that it's the task object you await, it's not the method. So if you look at this is what people often write. So we have an async method here, and we have another little helper method. And what you will often find is you'll say public async task, blah, 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 and then you return await and task. And then you say up here, I need to await. And people think about, I'm awaiting this method. But actually you're not. This method, once it's been rewritten, will return a task object, and you await the task object that gets returned. Now you can write this code yourself like this instead. In this scenario, you could just say, well, I'm not going to make this method async. I'm just going to return the task directly. You're just going to return the task object, and this code will just await the object in exactly the same way. The async keyword is really there just to tell the compiler that this method needs to be rewritten to look for anything awaits, and then wrap things into a callback, and then return a task object from the method. It's a compiler directive, if you like. Probably abusing that phrase, but hopefully you get my drift. As an aside, according to James Newton King, in his test, this code here takes about 11 nanoseconds, and this code here takes about 2 nanoseconds. This is when I mentioned in the introduction video that sometimes async is a bit slower. This is one of the examples of that, where because the state machine has an overhead, and that's a measurable overhead because you have to have these state machines that have to, and the code is just more complicated to run, even though this doesn't actually even do thread switching. It's literally just having a state machine that it needs to play around with. Okay. So, if you'll forgive the terrible pun, let's just talk about threading in async. If you are used to doing async in JavaScript, then you will know that it's really quite a simple model because JavaScript is inherently single-threaded. You still have callbacks, but the callback will basically be queued up and sit and wait on the event loop till the next time everything else is finished, and then it just sits in a queue and waits, and then it gets executed the next time the thread is free to run it. So that's, for example, in JavaScript, if you do like a timeout, an asynchronous timeout, then your callback will happen after the time you specified, or more specifically, it will take at least as long as you specified, but it might take longer. If the thread is busy when your callback comes back, it will just have to wait until it happens. This is quite different from .NET, where the callbacks will actually run on another thread. So yes, there are threads in async code. In .NET, you do have to think about threading. The important thing here is it sort of makes the conversation about the difference between Node and ASP.NET and ASP.NET Core a bit disingenuous. The performance conversations are very real, but when you talk about the coding model, in all honesty, the Node coding model is simpler because you really don't have to think about threads ever, whereas in ASP.NET you do still have to think about threads even if you're writing async code. I just want to cover thread pools because it's important to understand some of what I'm going to talk about, and especially if you want to test some of it. So the .NET application always have two thread pools as standards. Now we looked before at how long it takes to create threads, so you can understand why we want to use a thread pool so that we don't have to carry the overhead. And basically a thread pool is something that .NET keeps for you, so you can just say, I would like a thread please, and then you will get one of the threads in the thread pool. There are certain settings you can play around with, but I'll come on to that. The main thing is to understand that the worker thread pool is the main one. IIS uses it. If you're calling task.run, that means you're scheduling code to run on a worker thread. There's also the IO completion port thread pool. That's where the asynchronous callbacks runs on, so you can configure different settings for the two. You shouldn't really worry about it normally changing it, except for when you're testing some of this stuff. And also, I've sort of heard the IOCP threads referred to as lightweight threads and so on. As far as I can tell, there's absolutely no difference. They're just threads. They just happen to be in two different thread pools. If you need to tweak them, so there's a few things to understand here. A thread pool has a minimum and a maximum number of threads. The minimum number does not mean that, if you set the minimum to 1,000, it does not mean that you're going to get 1,000 threads created straight away. It's just that if say your min threads is 10 and you have already got 10 threads running and you come and ask for another one, then the thread pool will just wait sometimes a few hundred milliseconds until before it creates a new thread. But up to the minimum threshold, it won't wait at all. So for the first 10 threads, if you set it to 10, as soon as you ask for a thread and the existing ones are busy, you will get a new thread instantly. So for a lot of the testing I'm talking about with async, it's usually a good idea to increase the min threads, and in this call here, set min threads 2020 will set the min thread on both thread pools. I don't recommend you mess with this in production code, but unless you really know what you're doing. But for testing some of the scenarios, it's a really good idea because a lot of the issues I'm describing you won't actually see unless you have enough available threads in the IOCP thread pool. Now in your production code, that will probably be the case because you will have had a lot of callbacks happening and the number will have been creeping up. But on your desktop machine, when you're just starting from cold, you won't see that, and therefore you will have a delay, and therefore you won't see the concurrency issues that you will see in your production code. So just coming back to what we talked about before. So remember this bit of code, this bad pseudo rewritten code, where the compiler has rewritten your code to say, I'm creating this task object, this is the call and this is the callback. The important thing to understand is that this is your callback, and that will run on an IOCP threads pool if you're in a console app or an ASP.NET app. And according to my understanding, on an UI app, it will run on the UI thread, but I have to stress I'm not an expert on sort of desktop code and those kind of things. I mainly work on web stuff. But crucially, this code run on your on a separate thread to your main thread, if you like. So if we have a look at a console app and an ASP.NET Core app, so it's written as a console app, but the principles apply in ASP.NET Core. So what we're doing is we have an async method I've called a caller here, which calls this other async method and then awaits it. This thing here, creates an HTTP client, goes and does this thing, and then returns some data about it. And yes, I know you should never new up HTTP clients now. You should use the factory, but park that for now. Not relevant to this conversation today. So what will happen is you start running this code on the main thread, or if you're in ASP.NET Core, it would just be allocated a thread from the worker thread pool. So that's fine. We're calling into our caller method. So we go down here, and this code is still running synchronously on the main thread. We're going into the method, and we get to here where we're calling the get something method. So again, we go into that code, still running synchronously in the main thread. We create this thing here. We are creating the client here, and then at this point we get to this await statement. So the compiler will now rewrite this code, and all of this code here will be put into a callback. Control will be returned back to here, and because in this console app we're having a .wait, means we'll wait for that task to complete. If it had been in ASP.NET Core, we would have done an await on the return task object and given the thread back to the thread pool. But again, the principle applies. Now, at some point, this call will return, and this callback here that the compiler created for you will be then run on a IOCP thread pool thread, a background thread. So that, let's call it thread number 1. It can be any thread ID, but and then that will then return. Then, if you remember this await here, so this code here got written into another callback. That will then be invoked on another thread. It might be the same thread, it might be a different thread, but the point is, if it's the same thread, it's just because it happens to be available and it happens to be allocated to it, but it's another callback, it's another state that has to be unloaded and then a thread allocated to it. And then finally, we return back up to the main thread here, or if this had been ASP.NET Core, we would have had another callback here running on thread number 3. So that's console apps and ASP.NET Core. This works somewhat differently in the older ASP.NET. So different example for this one to try and explain what's going on. So we have a controller method here, and I'll just say, okay, that starts running on, let's just say thread number 1. So we have a method called here get content length. So that's happening here. We go into that method here, and that's still running synchronously on the initial thread. We create our HTTP client, and then this call here will await. The code will obviously go into get string async, but that's not our code, so we can't see that. So at this point, control will jump back to here, and the task that's been returned, because remember the controller rewrote the get content length method, that task will have been put into that variable here. We then go to the next line that calls get content length again, still running synchronously. We haven't done anything asynchronous yet, other than asking the operating system to do something, but the code is still running on the same thread. We go back in here, we're still running on thread number 1, we still create a new HTTP client, and then we jump back to here. Now at this point, we then go to await. So at this point, there's no more code to run, so your thread will be handed back to the thread pool. And at this point, there's no thread anywhere in your system that is allocated to this request. There's no IOCP thread, there's no worker request thread. This is the beauty of ASP.NET, because this is where it might take a while for these things to return and you're not blocking the threads. This is why you get your scalability. So that's beautiful. Okay, and then what will then happen, and this is quite important, in standard ASP.NET, without anything special, Now, when one of these calls return, and it can be either one, this code now wants to run. This is your callback code, but that will want to do a lock on the request context. So that's being used as a synchronization mechanism to avoid your callbacks to run in parallel with each other. So this is how ASP.NET, the old version, by default ensures thread safety of your asynchronous code by making sure that your callbacks can only run one at a time. And it's basically locking on the original request context that your request came in on. So it's locking on the state, if you like. Again, I'm oversimplifying the reality, but for the purposes of this, it should suffice. So that gets a lock on that. It runs this code, and then it returns up to here. So we now have this resulted. And then this code here will then run on, that's another callback. If you remember, all of this is one big callback. So that will then run on another thread. Then we get the other task returning, and that will then run on yet another thread, again locking on the request context. And then that will return up to here. And then this thing here will then, that's another callback for this nested within that callback, and that will then run on yet another thread. Now, as I said before, you can actually end up seeing this running all on the same thread or all on different threads. But the point conceptually, that's all different threads. It just gets the next available thread from the thread pool. So this is all fine. You can see it's quite complicated. There's a lot going on under the covers that you can't normally see. Now, if we change this very slightly, we add a configure await false in here. What that means is that we don't care about this request context for this callback. We're just saying this is a little thing that says, oh yeah, when you create the callback, this thing will not lock on the request context. Just run it as soon as you can. So imagine, so we do this, doom, thread one, thread one, thread one, thread one, exactly the same as before. This is all the same so far. But now imagine that these two different tasks, they return at exactly the same time. What you will find is that their callbacks will run in parallel with each other. So there are two different threads simultaneously running the same bits of code and modifying the same, potentially modifying the same state. In this case, there is no shared state, there's no threading issues here, but if some of this was referencing updating an instance member, for example, like in the example we did in our brain teasers, then you might have problems. So configure await is good, but it can make your code multi-threaded where it wasn't before. So you've got to be slightly careful with it. Again, most production code, most code is not an issue, but you know, it's something to be really quite aware of, and something that a lot of people don't really appreciate. And again, this is the default in ASP.NET Core, by the way. So in ASP.NET Core, this will always be multi-threaded code, and mostly it's not a problem because usually there's enough timing differences that it's fine. But you could have scenarios where, like in production, it starts being a problem, but you can't reproduce it, so you get into those Heisenbergs kind of thing. And any kind of debugging, even a logging statement in here, will usually throw off the timings enough. So yeah, proper Heisenberg territory, this stuff. Really something to be quite conscious of. Okay, desktop apps. I don't write Windows or Windows mobile apps, so I don't know this that well. I do apologize. But in a nutshell, desktop apps have a UI thread running. Form controls can only be updated on the UI thread. So async event handlers, they return on the UI thread so they can safely update control. This is what makes the async paradigm so attractive for writing desktop apps and Windows Phone apps, because it used to be much more complicated to do those handing control back from a worker thread and handing the data back to the UI thread to then update the controls, whereas with async it just hides it all away and is really quite nice. If you're having event handlers, my recommendation is to always put configure await on there anyway, whether you want it to be true or false, but you can have a rule to say you must always have it. If it's in an event handler, it should be true. If you're having other code that doesn't update controls, code that is just sitting in the background, probably a good idea to use configure await false on those. So that way you can, you know, make your code run a bit more parallel, not block the UI thread running callbacks that don't need to run on the UI thread.